Okay, just going to do Vesper. All right, everybody. So I'm going to briefly describe what Vesper is and how to predict the structure. This is, of course, after you practice drawing the Lewis dot structures, because if you haven't practiced being able to show bonding pairs and then the lone pairs of electrons, you're going to have a much harder time predicting what the valence shell electron pair repulsion structure is going to be. For those of you at Cumberland County College taking Chem 102, this is one of the first activities that you will do, but we like to overlap it so that way you can understand, you have a better understanding of what it is that's required. So, don't mind what's on the screen. I'm just trying to organize where I'm going to start. So basically, because of the law of electrostatics, there's going to be maximum separation upon the electron pairs within an atom. And we use this to predict molecular geometry. So if we go back to the slideshow, I'm probably going to go a little too far. There's resonance, resonance, formal charge, formal charge. Okay. So what does VESPR stand for? Valence shell electron pair repulsion. And the structure around a given atom is determined principally by minimizing electron pair repulsions. We basically have to look at the number of non-bonding pairs of electrons and bonding pairs of electrons. Remember, non-bonding are also known as lone pairs. And then we use these numbers to predict the approximate molecular structures. So VESPR is a three-dimensional arrangement of the atoms. We have linear, trigonal planar, tetrahedral. We also have varieties in between, depending on how many bonding and non-bonding and total pairs there are around what's called the central atom. Notice that in a linear structure, the molecule has a 180-degree bond angle. The trigonal planar has 120 degrees, and tetrahedral has an angle of 109.5. So to apply the VESPR model, we're not really taking any new steps. We're just adding a step. So the first thing to do is draw the Lewis structure for the molecule, count the electron pairs and arrange them in a way that minimizes repulsion, determine the positions of the atoms from the way electron pairs are shared, and determine the name of the molecular structure from the positions of the atoms. So for example, if we look at water, water has two lone pairs of electrons and two bonding pairs of electrons. Okay, so the bonding are here and the non-bonding are here and there. It has two bonding pairs, two non-bonding pairs. So that would relate to a tetrahedral structure, so that the atoms in the water molecule actually form what's called a V-shaped tetrahedral. So before I move on further with more examples, I'm going to show you this chart. This chart is one of the more helpful things. This tells you the number of bonding groups or domains on the central atom. So this is the total number of things around the central atom. So this includes the sum of the bonding and non-bonding pairs of electrons. This tells you the number of lone pairs of electrons on the central atom. And based on these two numbers, you can determine what the actual geometry is. Okay, so there's electron pair geometry and molecular geometry, and then what the bond angle is. So if we have two things surrounding the central atom, so these don't include the central atom, but no lone pairs, we say it's linear, which means that the bond angle is 180 degrees apart. So take a look at that image. There you go, 180 degrees. Central atom, one, two things around it, no lone pairs. Here are some examples. Beryllium hydride, carbon dioxide, acetonitrile. Next, let's add one thing around it. So now we have three things around it. It's going to be three bonding groups and no lone pairs. So therefore, we're going to have a trigonal planar. Trigonal planar means it's going to have a bond angle of 120 degrees between the atoms. So take a look at this structure here. Here's our central atom. All of these bonding pairs are 120 degrees apart. Oop, it's not where I want to go back to. Okay. What if we have 3 total things around the atom? 2 bonding pairs and 1 lone pairs of electron. We call that trigonal planar bent. Notice that the only difference is that for the trigonal planar molecular geometry, there's 0 lone pairs. For a bent trigonal planar, there's 1 lone pair, but there's still 3 things around it. Notice that the bond angle goes from 120 to less than 120. So if you're worried about memorizing, there's not a lot of memorizing. You just have to notice the patterns. Okay, 3 plus 0 equals 3. 2 plus 1 equals 3. 3 equals trigonal planar, 3 things around the central atom. And you can have either a trigonal planar or a bent. So what does the bent look like? Looks pretty much like the tetrahedral planar, except that there's going to be an electron pair over here. Now let's add another group around the central atoms. Let's go to 4. If we have 4 bonding pairs and 0 lone pairs, we say that that is tetrahedral. Tetrahedral has an angle of 109.5. 1, 2, 3, 4. Let's replace one of those bonding groups with a pair of electrons. 3 plus 1 makes 4. That's tetrahedral. And we say that the molecular geometry is called trigonal pyramidal. Basically, just take off one of these and replace it with a pair of electrons. Notice that the bond angle is less than 109.5. Let's take off another bonding pair and replace it with a pair of electrons. There we go. We've got 2 plus 2 equals 4. We call this bent. All we did was pluck off one of those bonding angles and replace it with a lone pair of electrons. We call this tetrahedral bent. Notice that for VSEPR, it keeps going. So that we have then, if we have 5 things around it, so we have 5 and 0, 4 and 1, 3 and 2, and 2 and 3. All 4 of these make trigonal bipyramidal, but then the molecular geometry changes depending on how many lone pairs we replace a bonding pair with. So trigonal bipyramidal has 5 bonding pairs and 0 lone pairs. Let's take a picture. It's trigonal bipyramidal because if you look at the plane, it makes 2 pyramids. So there's a pyramid on top and a pyramid on the bottom. All right, let's pop one of those off and make it a lone pair. We get what's called a seesaw. I'll pop another one off for a lone pair. T-shape. I think that's pretty self-explanatory. It makes a T. And then if we have 2 bonding pairs and 3 lone pairs of electrons, it's called linear, but it's going to be trigonal bipyramidal linear. Notice the angles. 90, 120, and 80, 90, 120, and 80, 90 and 180, 180. Finally, if we have 6 things or 6 bonding pairs around the central atom, no lone pairs, we call that octahedral. 5 bonding pairs and 1 lone pair is square pyramidal. Notice the square. There's a square bottom of the pyramid. 4 bonding pairs and 2 lone pairs makes it square planar. I think that is also self-explanatory. Okay, so those are the various types of molecular geometry. So let's go through some more pictures because I think that's what really does help. So this is our linear. Okay, notice 2 atoms around the central pair. Trigonal planar. This is 3 bonding pairs, 0 lone pairs. This is tetrahedral. 4 bonding pairs, 0 lone pairs. 5 bonding pairs. trigonal bipyramidal, because if you take a look and you can make a pyramid on the top and a pyramid on the bottom. Octahedral has 6 bonding pairs. Okay, just another chart showing you about the electron domains. But what happens if we take away the bond and we replace it with a lone pair of electrons? So if I can maximize this. All right, there we go. So this is known as a PhET simulation. I actually provide a link to it on Blackboard for you guys. You can actually play around with all of the different molecular geometries and kind of move it around. That is one of the best ways to learn about the geometries that you have to learn. So if you notice, these are 3 bonding pairs attached to the central atom that's purple. If we pop one of these off and we add a lone pair, the lone pair looks like the little alien head with the 2 little yellow eyes on it. So if you pop it off, you could see that that electron pair is going to push the other 2 bonding pairs away because it's going to take up more room. So this is what trigonal planar looks like, and this is what trigonal planar bent looks like. Still 3 things around the central atom, but one is a lone pair of electrons instead of a bond. Next, we have tetrahedral. Tetrahedral has 4 atoms, 4 bonding pairs. If we remove a bonding pair and replace it with a lone pair, we get trigonal pyramidal. If we replace it another bond with 2 lone pairs, a pair with another, so that we have a total, of 2 atoms and 2 lone pairs, then we get what's called tetrahedral bent. So here you go. This is tetrahedral, 4 bonds. Take away 1, add a lone pair of electrons. There's a little alien head. Now we get trigonal pyramidal. Notice it makes a pyramid. Again, the bond angle is going to be less than 109.5 because those electrons are going to take up more space. If we go to tetrahedral bent, we take off another bonding pair and replace it with another lone pair of electrons. Okay, now let's get to 5 things around the central atom. We have trigonal bipyramidal, which is 5 atoms. Seesaw means you have 4 atoms and 1 lone pair. T-shape is 3 atoms and 2 lone pairs. And linear is 2 atoms and 3 lone pairs. Again, notice that all you're doing is removing a bonding pair and replacing it with a lone pair each time. So here you go. This picture shows you the trigonal bipyramidal. 1, 2, 3. There's 1 back there. That's 4. And then this one is 5. Take 1 off. 1, 2, 3, 4 bonding. And the 5th is a lone pair. There you have seesaw. Over here is going to be T-shaped because now you have 1, 2, 3 bonds, 2 lone pairs of electrons. And over here we have 1, 2 bonding and 3 lone pairs of electrons. Finally, we have octahedral, 6 atoms. Every time you take away a bonding pair and replace it with a lone pair, you get a different molecular geometry. Square pyramid, square planar, T-shape, and linear. So here's our octahedral with 6 bonds around it. Here's our square pyramid where we now have 5 bonds and 1 lone pair. Square planar is 4 bonds and 2 lone pairs. T-shape is 3 bonds and 3 lone pairs. And linear is 2 bonding and 4 lone pairs. Here is a nice chart that I like to use. So that way it tells you the steric number is just the number of groups around the central atom total. And this is what happens if you have 0 lone pairs and just 2 bonding pairs. This is 3 bonding pairs, 2 bonding pairs and 1 lone pair, 4 bonding pairs, 3 bonding, 1 lone pair, 2 bonding, 2 lone pair, 5 groups, 6 groups. Okay. All right. That's the end.